Let's look at a method of joints example. So this is a simple little truss. Let's find the forces in each member of this truss. So we have AB here and then BC. Those are collinear to each other. Collinear to each other. CD and then AD here. There's a 20 kip load acting at D to the right. And this member BD comes down and attaches to this ABC at a 70-degree angle. We have 3 feet between the supports and point D on each side, to the left and to the right, and then it's 4 feet tall. Are there any zero force members? Well, of course there are, because I was kind of giving you a strong hint. AB and BC are collinear. BD is non-collinear, and at joint B, there are only 3 members framing in, 2 of which are collinear, and there is not a support reaction there, and there is not an applied load, so BD has to be a zero force member. So after we find all the zero force members, in this case there was just 1, now after that we'll calculate the reactions. We don't necessarily have to always calculate reactions. As a matter of fact, for this particular problem, there is a scenario where you wouldn't even need to calculate the reactions. But like I mentioned earlier, it's always just good, especially if you don't know where to start, calculate some reactions. It's a great way to get your kind of feet wet in a problem, and it also tells you a lot about what the next step could be, which is to solve the truss. All right, like I said, BD is a zero force member, so we're going to put a big 0 through it. It might as well not even be there anymore. As a matter of fact, I think in my subsequent free body diagrams, I might not even show it. So to find our reactions, first off, we got to draw our reactions, right? Because until I give it an arrowhead and a direction, I don't know what I have. A is a roller, C is a pin. So at C, I'm going to have RCX. And then due to my Y direction, I have RA and RCY. Those are all my reactions that are happening. And now I can solve for my reactions. Since this is a roller right here, there's no horizontal reaction. It's pretty obvious that RCX is going to be equal and opposite to the applied load of 20 kips. But I went ahead and wrote this equation out just so you could see that. Sometimes you might see, and you might want to learn this for your future work, if there was something like this that is very plainly obvious, you could say RCX equals 20 kips, pointing to the left because we drew it to the left, but is equal to 20 kips, quote unquote, by inspection. And that just means, in fancy engineering speak, duh. It means I don't want to go through all of the handwritten work to say that. However, if you don't say something is equal to something by inspection, then you're not letting them know that you think it's duh. It's just not even being said. And so when you write by inspection, it is still a statement. You have decided that that member or that reaction or whatever, in this case, this reaction is equal to 20 kips, and we were saying that is true by inspection. In this case, I actually did write the equation, so then I wouldn't need to write by inspection. But I mean, I could have just written RCX equals 20 kips by inspection because there's only 2 forces going on. It's about as easy as statics get. Am I right? Let's write 20 kips over there. Keep our free body diagram updated. So we've got 0 here, 20 kips there. And now we can, there's actually several ways we could solve this. I'm going to do counterclockwise positive summation of moments about C. So I'm going to sum moments about the pin support over here, which is going to give me R sub A. All right. So for R sub A, I've got 20 kips times the 4 feet height. So that's here. And that's negative because it's clockwise. And then I have RA times 6 feet. That's its distance from C. It's also, since I had assumed it was pointing up, which is probably a bad choice, it's giving me a clockwise moment as well. So I have negative and negative. When you solve for this, it's pretty obvious that RA is going to end up being negative. So it's negative 13.33 kips, which actually means no big deal. I just picked the wrong direction. It's actually pointing down. I'm not going to change that because I wrote it here in PowerPoint, but I mean, you might have written it in pencil, hopefully, not pen, but some of you still write in pen. But you might have written it in a way that you don't want to erase it. especially if earlier calculations were kind of pointing to the fact that it was pointing up, and then all of a sudden you erased it and wrote it, the vector pointing down, then all your earlier work disagrees with what you just changed. So be careful of erasing vectors and switching their direction. If you do it, be very clear in what you're doing for yourself and for me and for everybody else so that you can make sense of your own work. It needs to be a logical progression. You're a storyteller when you're writing these calculations. So the way I like to do it, I'm saying it's minus 13.33 kips, which means 13.33 kips down, and I leave it pointing up. And if I need to go into any of my equations, it'll be easy enough to say, well, yeah, this is pointing up, and it has a value of minus 13.33 kips, and I can plug that into any equation pretty easily. So let's just write that on our free body, keep it updated. And then I can do sum of forces in the y. And this is exactly what I'm talking about. I'm saying up is positive. So I have an up pointing vector here, so it's positive, I suppose. Its value is minus 13.33. So that's why this minus will still make it into the equation. So that's why I don't really like to change the vector direction. It's all going to work out on the end anyway. Just be very clear and decisive in your free body diagrams and in your equations by picking what's positive, by showing what direction things are and what the sign is, and you'll get through it. So now I have minus 13.33 kips plus RCY, because it's pointing up, equals 0. That gives me that RCY is 13.33 kips. Whoa, wait a second. 13.33 kips down and 13.33 kips up. That is a force couple. This is one of those times where I said earlier in the semester, force couples show up all over the place. This is one of those. I have a actually the only applied load is in the X direction, and look at my vertical reactions. Not only are they pretty big, they're over half of the applied load, they are actually equal and opposite to each other. And really what's going on here is these two reactions are counteracting themselves, right? If you have 13.33 kips acting up and you have no force pushing down, all of a sudden your truss is launching up into space. So this one over here is resisting against that. It all works out. But what it is doing is it's causing a counterclockwise moment. This force couple is causing a counterclockwise moment. And if you think about what I just did about C, this 20 kip load times 4 feet is actually wanting to cause a clockwise moment. So that's why they're there. Okay? Force couples are going to show up all over the place, especially in trusses, but all over the place in statics and in your future coursework. So to continue our solution here, you're going to start finding that in trusses especially, and a method of joints especially, there might be hundreds of solution variants that are going to happen. So this is just the one that I'm picking. There's really only a few different choices you can do for this truss because there's only 3 nodes and 3 members. But here's the one I'm going to do. I found my reaction at A. I'm going to draw a free body diagram at A. And this is my free body diagram at A. Sum of forces in the Y equal to 0. I've got pointing up minus 13.33 kips, and then I've got plus 4/5 of FAD equal to 0. Solve for that. I get that FAD has to equal 16.67 kips. I put that value up on the free body diagram. And since it was positive, that also means that it is tension, because I drew it positive pointing away. My unknowns are pointing away. I drew them in the correct positive sense so that it gives me, when it's a positive number, it means tension. Let's do sum of forces in the X now. I've got 3/5 times the 16.67, which I just learned from my previous equation. And then I've got plus FAB equal to 0. RA does not enter into this equation because it is acting purely in the Y. I solve for this and I get minus 10 kips. What does the minus mean? It means that this vector is pointing the wrong way. Fine. It also then means that it is compression, because a member that is pulling on a joint is in tension. A member pushing against the joint is in compression. Taking these values here that we've learned, let's go and move on to the next joint. Again, there's probably other ways that this could be done. Let's look at the free body diagram at joint D. So the free body diagram at joint D, they're both on a 3, 4, 5 force triangle. This one we actually have learned from our previous slide that it is 16.67 kips. See how it's pointing away from this joint, just like it was pointing away from joint A. That's what I was saying earlier. When you go to the other end of a member, the arrow flips direction. FCD, we don't know which way it's going yet. We're drawing it positive, pointing away. 20 kips is our applied load. We are keeping the parts that we're keeping. Joint D, these little stubs of member coming off, the geometry associated with that, the 20 kip load. And we get rid of the parts we're getting rid of, the reactions, the other member. And we replaced the parts we got rid of by putting internal force vectors at the cut locations. And so we're following all the rules here. You might say, well, what about that zero force member right there? Remember, it was zero force, so I chose not to draw it. It's better to just forget it ever happened. Summing forces in the X at D can get us what we need because we only have one unknown in the X. We could have also have done in the Y. It would have been just as good. Actually, potentially even easier now that I'm looking at it, because we would have only had two unknowns. Whatever. Once you get used to this, you'll see that even if you don't necessarily pick the fastest route every single time, as long as you're drawing your free body diagrams right, you will get a correct route. So I get that FCD had to be minus 16.67 kips, and that negative means compression. And so then our table here of answers, I have all of my members shown. AB was 10 kips of compression, as was CD was 16.67 kips of compression we just drew. AD was 16.67 tension, that's this one. BD was that zero force member. And then BC is actually the same as AB. They're both 10 kips in compression. And that's because they're really just, since that member that went across the middle was a zero force member, really that entire bottom member was all the same member. So AB and BC, if this member is not even here, it's almost like there's really just the member AC.